There's a lot more to talk about in how we organize and address data in memory. Let's start with a very important distinction between addresses and pointers. You'll notice that I've drawn a memory on this slide that has bytes grouped into 4-byte units that are our 32-bit words. You'll also notice that the first word is shown at address 0, the second word at address 4, then 8, and then C. This is now in hexadecimal notation, so C corresponds to the decimal 12. Hexadecimal 10 corresponds to the decimal 16. So here we're adding 4 for each address as we move down our memory, since we're talking about words. In this particular case, I've shown you the detail of one word that happens to have the value 0001015F in hexadecimal. That corresponds to the decimal number 351. Now, an address is a location in memory, as we've said. So we have these different addresses here from 00 hex to down to 24 hex for all these various locations in memory. A pointer, unlike an address, is a data object that contains an address. So let me give you an example. I can put a pointer to that address of 0004 at a different memory location, let's say at the address 001C. So now you'll see that what I've shown in the memory is that at that location, 001C, I have a value that happens to be the address of another location in memory. That's what makes it a pointer, the fact that I interpret it that way. I could have just as easily have interpreted that number as just the number 4. That would have been a data value stored at that location. But I am now choosing to interpret it as an address, in which case it is a pointer to a different location. Let's take a look at another example. I can have a pointer to that location in the address 0024 by placing the value 0000001C at the location 0024 in memory. Again, I am choosing to interpret this as an address, therefore it is a pointer to another memory location. If I had interpreted as just a number, what number would it be? It would be the hex number 1C, which is 16 plus 12, or 28 decimal, and not an address. Okay, so it's purely an interpretation question. Will I interpret this value as a pointer and therefore an address to another location, or will I interpret it as a value? That's the distinction between addresses and pointers. Another example is if in that memory location 0014 I had put the value 0C. Well, is that an address? Well, it could be an address. It's part of our memory, certainly. There is a word with that address, but am I interpreting it as an address? Well, I may be, or it may be just the number 12 corresponding to that hexadecimal C. In C and in Java, we have many different data types, and how we represent them in our machines varies because of the amount of bits that we need to represent them. So this table just gives you a quick comparison of how that's done in both a 32-bit machine and a 64-bit machine. So you'll see that a Boolean data type requires just 1 byte. Now, in reality, we could probably do it in 1 bit, but it's since we address things in terms of bytes, it's going to take up 8 bits to do that. A byte, of course, requires 1 byte. In C, a byte is also a character in a character string. Java has a more complex structure for characters that we'll get to a little bit later on. That takes up 2 bytes per character. A short integer or a 16-bit integer takes up 2 bytes in both, while a regular integer takes up 4. This is based on the fact that we have a lot of programs that were written for 32-bit machines. A floating point number also takes up 4 bytes. We'll discuss how we represent floating point numbers later. On 64-bit machines, we also have a long int data type, an integer that takes up 64 bits or 8 bytes. We also have double floats and long longs and long doubles that can be particularly large range of numbers, taking up 16 bytes. And then we have addresses or references or pointers, which in a 32-bit machine can be up to 4 bytes by definition, and in a 64-bit machine can be up to 8 bytes by definition. All right, the next question is, how do we order the bytes within a word? There's actually 2 ways to do that. One way is what's called big endian, and the other is little endian. And these 2 different conventions come from, the names for them come from Gulliver's Travels. You can read about this in the textbook by Bryan and O'Halloran that we're using as a reference text for this class. But basically, the idea is that in a big endian notation, the most significant byte of the number goes to the lowest address. And in the little endian notation, the least significant byte goes to the lowest address. So let's do a quick little example to demonstrate that. Suppose I have the following 8-digit hexadecimal number, 0, 1, 2, 3, 4, 5, 6, 7. Okay? And I want to store that at a word at address 100 hex. Now, in a big endian computer system, it would be stored as follows. Okay? The most significant byte, in other words, the highest order digits, go to the first byte. Then the next 2 go to the next byte, and so on until the lowest significant digits go in the last one at 103. In little endian notation, well, it's the opposite order. The lowest order digits come in first at address 100, and the highest order digits end up going at 103. These are the 2 natural choices to do, and you notice that the little endian one looks a little backwards from our original number, but that is in fact the one that the x86 architecture uses. So that's what we'll be seeing a lot in the memory maps that we'll be looking at, and when we look at memory values in memory, they will be arranged this way. Just a quick another example, looking at the decimal value 1, 2, 3, 4, 5. In binary, that's represented right below as those binary digits, which are the hex 3039. Okay, so you'll see that in a 32-bit architecture, we put the least significant digits at the lowest address and the most significant digits at the highest address, while it's in the opposite order on a big endian architecture. For a negative number, and don't worry about this right now, but this is the number minus 1, 2, 3, 4, 5, represented in 2's complement notation that we'll get to a bit later. But again, the lowest significant digits are represented first, while in the big endian it's the other way around. Now here you'll see why little endian might be somewhat advantageous. In a 32-bit architecture to a 64-bit architecture, you'll notice that the correspondence of those locations is the same, when then there's a lot more zeros, of course, in the 64-bit notation to pad things out. While in the big endian notation, we can't just simply extend in this direction with zeros. We have to actually go in the other direction and move this down, which is a bit more complex.